Today, we start not with complex equations or strange particles, but with a single, deceptively simple question that, once asked, creates a hairline fracture in the foundation of your reality. A question that a handful of physicists in the early 20th century were forced to confront, and question that led them down a rabbit hole from which they and all of science never returned. The question is this: what is anything, really, when you're not looking at it? Think about that for a second. Not in a deep, poetic way, but in a literal, physical way. That chair you're sitting on, you see it, you feel it, it's there. But what is it doing when you leave the room? Common sense screams that it's just sitting there, existing, maintaining its chair-like properties. It has a specific location, a specific shape. It is, unequivocally, a chair. Quantum mechanics whispers that common sense is dead wrong. And to understand how, we need to meet the first ghost that haunted the halls of physics, a ghost that, to this day, has never been exorcised. Our story doesn't start in a futuristic lab, but in the warm, glowing heart of a 19th century mystery. Scientists were obsessed with what they called black body radiation. Imagine a perfect object that absorbs all light and heat that hits it, and, when heated, emits a perfect spectrum of that energy. Think of a piece of iron in a forge. As it heats up, it glows red, then orange, then yellow, then white. Classical physics, the physics of Newton and Maxwell that had so elegantly described planets and light waves, had a beautiful equation to predict this glow. There was just one tiny, catastrophic problem. The equation was wrong, spectacularly wrong. It predicted that as you looked at shorter and shorter wavelengths moving from red light to ultraviolet and beyond, the energy emitted would become infinite. This was the ultraviolet catastrophe. It meant that every object, at every temperature, should be blasting out an infinite amount of high-energy radiation. You would be vaporized by the ultraviolet light coming from your cup of coffee. Obviously, this wasn't happening. The real world showed a nice, tidy curve that peaked and then fell off. Classical physics was not just a little off. It was, fundamentally, brokenly, embarrassingly wrong at the atomic scale. The year was 1900. A physicist named Max Planck, a conservative man who loved the established laws of physics, was desperate. He didn't want to overturn classical physics. He just wanted to fix this one nagging problem. So, he did something he considered a mathematical act of despair. He proposed a hack. He suggested that energy wasn't a continuous, flowing stream, as everyone had always assumed. Instead, it could only be emitted or absorbed in tiny, discrete, indivisible packets. He called these packets quanta. The idea was radical. It was like saying water could only exist in specific, fixed-sized droplets, and you could never have half a droplet. It made no common sense. But the moment he plugged this quantization into his equations, the infinite energy problem vanished. The math perfectly matched the experimental data. The curve fit. The catastrophe was averted. Planck had no idea what he had done. He saw it as a mathematical trick, a convenient fiction to make the numbers work. He spent years trying to reconcile his quanta back into classical physics, to find a way his hack wasn't real. But the genie was out of the bottle. Enter a young, brash patent clerk in Switzerland, a man with wild hair and an even wilder imagination, who saw in Planck's desperate hack not a trick, but a profound truth about the universe. His name was Albert Einstein. In 1905, his miracle year, Einstein took Planck's idea and ran with it. He applied it to a different puzzle, the photoelectric effect. Scientists had found that when you shine light on a metal, it can kick out electrons. But the behavior was bizarre. Increasing the intensity of the light, making it brighter, didn't kick out electrons with more energy. It just kicked out more of them. However, changing the color of the light, shifting to blue or ultraviolet, did increase the electron's energy. This made no sense if light was a continuous wave. A more intense wave should carry more energy, like a bigger ocean wave hitting the shore. Einstein's solution was breathtakingly simple and utterly heretical. He said, light itself wasn't just emitted in packets. It existed as packets. It was a particle. He called these particles of light photons. Each photon carried a specific amount of energy, determined by its color. A blue photon packed a bigger punch than a red photon. In the photoelectric effect, a single electron is knocked loose by a single photon. A brighter light just means more photons, knocking out more electrons. But a bluer light means each photon has more energy, so each electron gets kicked out harder. The physics community was aghast. Light was a wave. This had been proven beyond a shadow of a doubt by a century of experiments showing interference and diffraction. Thomas Young's double-slit experiment was a cornerstone of physics. And now this upstart was saying it was a particle. But Einstein was right. His explanation fit the data perfectly. For this work, he would later win the Nobel Prize. The universe, it seemed, was schizophrenic. Light was a wave. Light was a particle. This was the first major crack in the edifice of common sense. Things were not what they seemed. The solid, predictable world was beginning to look a little fuzzy. While Einstein was unraveling the nature of light, another puzzle was consuming physicists, the atom. The prevailing model was the plum pudding model, proposed by J.J. Thomson. It pictured the atom as a diffuse, positively charged pudding with tiny, negatively charged electrons embedded within it like plums. Then, in 1909, Ernest Rutherford, with his colleagues Hans Geiger and Ernest Marsden, conducted one of the most famous experiments in history. They fired tiny, positively charged alpha particles at a thin sheet of gold foil. According to the plum pudding model, these particles should have passed straight through with only minor deflections, like a bullet passing through a cloud. But that's not what happened. Most of the particles did indeed zip right through. But to everyone's astonishment, a few of them bounced straight back. It was, as Rutherford famously said, as if you had fired a 15-inch naval shell at a piece of tissue paper and it had come back and hit you. This was impossible under the plum pudding model. The only way a particle could bounce back was if it had hit something incredibly small, incredibly dense, and positively charged. Rutherford had discovered the atomic nucleus. The atom was mostly empty space, with a tiny, massive nucleus at the center, and electrons whizzing around it. This solved one problem, but created a far worse one. According to the well-established laws of electromagnetism, an accelerating charged particle, like an electron orbiting a nucleus, should continuously lose energy by emitting radiation. It should spiral into the nucleus in a fraction of a microsecond. Every atom in the universe, and therefore the universe itself, should have collapsed in a flash of light. The fact that you and I exist is proof that this doesn't happen. So, why don't atoms collapse? The man who stepped in to solve this was Niels Bohr, a visionary Danish physicist. Bohr looked at the problems with the Rutherford model and the strange success of Planck and Einstein's quanta, and he had a stroke of genius. He imposed quantum rules on the atom itself. He proposed that electrons couldn't orbit the nucleus at just any distance. They were restricted to specific, discrete, allowed orbits or energy levels. Think of it like a ladder. You can stand on the first rung, the second rung, or the third rung, but you can't stand between rungs. An electron in an allowed orbit, bizarrely, does not radiate energy. It's stable, but here's where it gets really strange. Bohr said an electron could only jump from one allowed orbit to another. It couldn't glide smoothly between them. When it jumped to a lower orbit, it would emit a single photon of light with an energy exactly equal to the difference between the two orbits. When it absorbed a photon with just the right energy, it would jump up to a higher orbit. This was the birth of quantum mechanics. It was a hybrid, awkward model, patching classical orbits with quantum rules. But it worked. It perfectly explained the spectrum of hydrogen, the unique fingerprint of light that hydrogen gas emits when energized. The equations matched. The predictions were stunningly accurate, but the cost was our common sense. Bohr was saying the universe was digital, not analog. An electron doesn't smoothly change its energy. It teleports from one state to another. It exists here or there, but never in between. This quantum leap is not a large jump, it's an instantaneous, discontinuous transition with no path in between. The universe, at its fundamental level, was pixelated. Bohr's model was a triumph, but it was also deeply unsettling. It raised a question that was even more profound than the one it answered. Why these specific orbits? What law of nature forbids an electron from existing in the gap? The model provided the what, but the how was a complete mystery. The ghost in the machine was no longer just a faint whisper. It was now speaking in clear mathematical sentences. And what it was saying was utterly bizarre. To show how absurd he found this idea, Schrödinger devised a gruesome thought experiment. He asked us to imagine a steel chamber. Inside this chamber, we place a single radioactive atom. We hook this atom up to a Geiger counter. If the atom decays a purely quantum, probabilistic event, the Geiger counter will click, triggering a hammer that shatters a vial of poisonous gas. Also in the chamber is a live cat. Now close the box. According to the Copenhagen interpretation, the radioactive atom is in a superposition. It is in a state of having decayed and not decayed. Its probability wave describes both realities simultaneously. But this atom is wired to the fate of the cat. Therefore, the entire system atom, Geiger, counter, hammer, poison, and cat must also be in a superposition. The cat, until we open the box and look, is both alive and dead. It is a blur of a living cat and a dead cat, a spectral feline existing in two mutually exclusive states. This, Schrödinger argued, is patently ridiculous. A cat is either alive or dead. It doesn't exist in a phantom state of alive deadness. The purpose of the thought experiment was to use our common sense about cats to show that the Copenhagen interpretation, when scaled up from atoms to everyday objects, leads to insanity for decades. This is how the story was told. Look how silly quantum mechanics is. It says cats can be dead and alive. But this misses the profound and terrifying point Schrödinger was actually making. He wasn't mocking quantum mechanics. He was highlighting a genuine, unresolved paradox. The paradox of where the cut is between the quantum world and the classical world. When does the superposition end? When the atom decays? No, that's just a quantum event. When the Geiger counter clicks? But the Geiger counter is made of atoms. Why can't it enter a superposition of clicked and not clicked? When the hammer falls? When the poison is released? When the cat's nervous system is affected? The chain is seamless. There is no clear physical line you can draw where the fuzzy quantum world stops and the definite classical world begins. So, if the math of quantum mechanics applies to the atom, and there's no physical reason it shouldn't apply to larger and larger systems, then the math says the entire box and everything in it must be in a superposition. The cat is a monster we created to hold a mirror to our own ignorance. The real question isn't about the cat's health. The real question is, what magical process breaks the superposition? What is so special about observation that it collapses the probability wave and forces a single reality to manifest? The Copenhagen interpretation's answer was vague and deeply unsatisfying. It essentially said, it collapses when it interacts with a classical measuring apparatus. But this is circular. What makes an apparatus classical? When does an apparatus become big enough to be classical? A single photon can trigger a measurement. This was a hand wave, a philosophical cop-out. The monster in the box wasn't the half-dead cat. The monster was the realization that our most fundamental theory of reality had a gaping hole where the observer should be. And into that hole rushed a host of even stranger ideas, frustrated with the vagueness of the Copenhagen interpretation. Physicists began to propose alternatives. These are not wild speculations. They are serious, mathematically consistent interpretations of the exact same quantum equations. They represent different answers to the question, what really happens during measurement? And each one is more mind-bending than the last. The first, and in many ways the most straightforward, is the de Broglie pilot wave theory. Louis de Broglie originally proposed that particles are real, point-like objects that have a definite position and trajectory at all times. But they are guided by the Schrödinger wave, which acts as a pilot wave. The particle is like a cork bobbing on a complex, invisible tide. In this view, the probability wave doesn't represent a lack of reality. It represents a real, physical field that guides the particle. The particle is always in one place, and the wave tells it where to go. This seems to rescue common sense. So, why isn't it the standard interpretation? Because the price you pay is non-locality. The pilot wave is an invisible hand that connects everything in the universe instantaneously. The path of one electron here can be instantly influenced by the wave generated by an electron on the other side of the galaxy. This spooky action at a distance was something Einstein hated even more than probability. But, as we'll see, this spookiness might be unavoidable. The second and most audacious interpretation is the many worlds interpretation. Proposed by Hugh Everett III in 1957, Everett took the Schrödinger equation at face value. He said, the equation never breaks. The wave function never collapses. So, what happens in Schrödinger's box? The atom decays and doesn't decay. The two possibilities don't collapse. They both happen, but they happen in separate, non-communicating branches of reality. When you open the box, you don't collapse anything. You split. In one branch of reality, you see a live cat and feel relief. In another, equally real branch, you see a dead cat. The universe constantly bifurcates at every quantum event, spawning a vast, ever-growing multiverse of all possibilities. Every time an electron has a choice, the cosmos forks. In one universe, you're watching this video. In another, you decided to get a snack instead. In another, the Roman Empire never fell. This solves the measurement problem by eliminating the observer's special role. There is no collapse because everything that can happen does happen, but the cost is ontological extravagance on a cosmic scale. It replaces the paradox of the cat with the silent, infinite schism of all reality. The question is, no longer is the cat alive or dead, but which one of the infinite versions of me am I? The third major contender is less a single theory and more a research program. This is the modern, and in many labs, the most favored approach to bridging the quantum classical divide. Decoherence doesn't so much solve the measurement problem as it explains why we don't see superpositions in everyday life. The key insight is that quantum systems are never truly isolated. A lone electron can maintain its delicate superposition, but put that electron near air molecules, photons, or any other environment, and it immediately starts to interact with them. These interactions effectively leak information about the electron's state into the environment. This process, called decay, destroys the quantum interference effects, the ability to be in two states at once incredibly fast. Think of it like this. It's easy to have a secret if you're alone on a desert island. But the moment you whisper it to one person in a crowded room, the secret is out. You can't take it back. The information has decayed into the environment. Similarly, a cat is constantly interacting with trillions of air molecules, photons, and the molecules of its own body. Its alive state and dead state become inextricably entangled with the environment almost instantly. The superposition still exists in a technical sense, but it's become a hopelessly scrambled, non-localized mess. For all practical purposes, it has collapsed into one reality or the other. Decoherence explains how the quantum world appears classical to us, but it still doesn't answer the deepest philosophical question. It tells us how the superposition becomes inaccessible, but not which of the possible outcomes becomes our reality. The choice of alive or dead is still left hanging, so we are left with a menu of bizarre options. Do we choose the spooky, guided particles of pilot wave theory, the infinite, branching realities of many worlds, or the pragmatic "it just looks that way" of decoherence? Each one saves the phenomena, but demands a radical revision of our worldview. And yet, for all their differences, they all point to a single, inescapable conclusion born from a simple experiment. An experiment that proves, beyond any doubt, that reality is not local, that what happens here can be connected to what happens there instantly. It's time to meet the experiment that Einstein feared, the one he called spooky action at a distance. By the 1930s, Einstein was deeply unhappy. He saw quantum mechanics as an incomplete theory. He believed that underneath the probabilities, there must be hidden variables, unknown factors that determined a particle's behavior, restoring a deterministic, common-sense universe. He, along with Boris Podolsky and Nathan Rosen, devised a brilliant thought experiment to expose what they saw as quantum mechanics absurdity. It became known as the EPR paradox. Imagine a single particle that decays into two smaller particles, A and B, according to the law of conservation of momentum. If particle A flies off to the left with a certain spin, particle B must fly off to the right with the opposite spin. They are entangled. Now, let these two particles travel light years apart. Now, a scientist on Earth measures the spin of particle A instantly. She knows the spin of particle B light years away. According to Copenhagen, before the measurement, neither particle had a definite spin. They were in a superposition of all possible spins. The moment she measures A, its wave function collapses into a definite state. And simultaneously, the wave function of particle B, no matter how far away, also collapses into the opposite state. Bohr's model was brilliant, but it was a bit of a fudge. It worked for hydrogen, but fell apart for more complex atoms. It was clear that a more complete, more radical theory was needed. The next great leap forward came from a French prince, Louis de Broglie, in 1924. De Broglie, in his doctoral thesis, made a stunning proposal. If light, which everyone thought was a wave, could behave like a particle, then perhaps things everyone thought were particles, like electrons, could behave like waves. Think about that for a moment. He was suggesting that an electron, a tiny speck of matter, wasn't just a little billiard ball. It was also a wave. A wave of what? He called it a pilot wave, or a matter wave. The idea was so absurd that his thesis committee didn't know what to make of it. They sent a copy to Einstein, who responded that de Broglie had lifted a corner of the great veil. It was enough to grant him his PhD. But was it real? Could a particle like an electron really be a wave? The test was simple. Waves interfere. If you send a water wave through two slits, you get an interference pattern of peaks and troughs on the other side. If you send a stream of particles through two slits, you just get two clumps. The definitive experiment to prove something is a wave is the double-slit experiment. So, physicists did it. They set up a double-slit apparatus and fired a beam of electrons at it. The result sent a shockwave through the scientific world. The electrons produced a perfect interference pattern. They were behaving like waves. This was monumental. It meant that the very concept of a particle was inadequate. An electron wasn't a tiny ball. It was a smeared-out wave of probability. But a probability of what? The answer came from an Austrian physicist, Erwin Schrödinger. In 1926, inspired by de Broglie's work, he derived an equation that described how these matter waves behave and change over time. The Schrödinger equation became the cornerstone of quantum mechanics. It is to quantum physics what Newton's F equals ma is to classical physics. But there was a problem. What was waving? It wasn't a wave of material like water. It wasn't a wave of energy like light. Schrödinger initially thought it might represent the actual physical smearing out of the electron's charge. But that interpretation quickly ran into trouble. The correct interpretation was provided by a German physicist, Max Born. He made what is perhaps the most important and most disturbing philosophical statement in the history of science. He said the wave described by Schrödinger's equation is a wave of probability. The wave doesn't tell you where the electron is. It tells you where you are likely to find it if you look. The peaks of the wave correspond to locations with a high probability of finding the electron. The troughs correspond to a low probability. Let that sink in. According to quantum mechanics, an electron does not have a definite position before you measure it. It is not somewhere. It is everywhere at once, a ghostly haze of potentialities, a cloud of maybe. It is only when you make a measurement, when you force it to declare itself, that this probability wave collapses into a single definite point. The act of observation forces a potentiality to become an actuality. This is where common sense doesn't just crack, it shatters into a million pieces. The moon is not there when you're not looking. In a very real mathematical sense, according to quantum mechanics, it isn't. It exists as a probability wave spread over a vast region of space. Its particles are in a blurred state of potential existence. Your observation is what nails it down. This is no longer just a weird fact about tiny particles. This is a statement about the nature of reality itself. Reality, at its most fundamental level, is not solid and deterministic. It is probabilistic and fuzzy. It is a set of tendencies, a landscape of possibilities. The solid chair you're sitting on is, at the quantum level, a chaotic, probabilistic dance of waves that only appear solid because of the sheer number of particles involved. We have traded a universe of clockwork certainty for a universe of quantum potential, and we are only just beginning to see the consequences. If the probabilistic nature of the quantum world was a body blow to common sense, the next discovery was a knockout punch. It came from a young German physicist, Werner Heisenberg. Heisenberg was trying to understand how to talk about quantum objects. If an electron doesn't have a position until you measure it, what can you actually say about it? In 1927, he formulated his famous uncertainty principle. The principle states that there are certain pairs of properties that you can never know with perfect precision at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know where it's going, and vice versa. This is not a limitation of our measuring equipment. It is not because our microscopes are too crude or our clocks are too slow. It is a fundamental, inescapable law of nature. Imagine trying to see a tiny electron under a super powerful microscope. To see it, you have to shine a light on it. But light comes in photons, and when a photon hits the electron, it gives it a kick, changing its momentum. If you use a very high-energy photon, like blue light, to pinpoint its location very accurately, you give it a huge, unpredictable kick, destroying any knowledge of its momentum. If you use a very low-energy photon like red light to gently probe its momentum, you get a fuzzy picture of its position. You can't win. This has profound implications. It means the universe is inherently fuzzy. There is a fundamental graininess to reality. You cannot have a world where every particle has a perfectly defined position and velocity, as Newton and Laplace envisioned. Laplace famously said that a vast intellect, knowing the position and momentum of every particle in the universe, could calculate the entire future and past. This idea, known as determinism, is the ultimate expression of a clockwork universe. Heisenberg's uncertainty principle murdered determinism. It is impossible, even in principle, to know both the present position and momentum of every particle. Therefore, it is impossible, even in principle, to predict the future with absolute certainty. The universe is not a predetermined clockwork. It is a game of dice. This infuriated Einstein. He spent the rest of his life arguing against this, famously stating, "God does not play dice with the universe." But every single experiment for the last century has confirmed that Heisenberg was right. God does play dice, and the dice are loaded in a way we are only beginning to understand. The uncertainty principle severs the chain of cause and effect at the most fundamental level. It introduces an element of genuine randomness, of irreducible chance, into the heart of physics. The future is not written. It is a tapestry of probabilities, waiting to be woven by the act of observation and the roll of the quantum dice. We have reached the end of this first, dizzying chapter. We have seen how light is both a wave and a particle. We have seen how electrons exist as probability clouds and teleport between states. We have seen how the very act of looking changes what we see, and how there is a fundamental limit to what we can know. But this is only the beginning. The rabbit hole goes much, much deeper. For if particles are just probability waves, and observation collapses them, a terrifying and exhilarating question arises, a question that will be the focus of our next chapter. We have dismantled the world of objects. Now, we must confront the one who is doing the dismantling. If the universe only becomes real when observed, what or who counts as an observer? Today, we cross into that uncharted territory. We are going to confront the possibility that the line between the observer and the observed is not just blurry, it might not exist at all. We will delve into an experiment so simple a child could understand its setup, and so profound that decades later we still haven't recovered from its implications. An experiment that suggests the mere possibility of knowledge is enough to change the past. And in doing so, we will be forced to ask a question that will follow us for the rest of this series. A question that strikes at the very heart of what it means to be a conscious entity in a quantum universe. Does the world exist when you're not looking at it? Or is your glance what brings it into being? To understand the problem of the observer, we need to meet its most famous and most misunderstood mascot, Schrödinger's cat, in 1935. Erwin Schrödinger, the man who gave us the equation that governs quantum waves, was deeply troubled by the direction his colleagues were taking. He, like Einstein, was a realist at heart. He believed the world existed in a definite state, independent of anyone looking at it. He saw the Copenhagen interpretation chint by Niels Bohr and Werner Heisenberg as a philosophical surrender. This interpretation stated that the probability wave wasn't just a description of our knowledge. It was the complete physical reality. Nothing was real until it was measured. But what if we could test this connection more directly? What if we could design an experiment to see if consciousness itself, the act of intention and attention, can reach down and influence the quantum world? This is not just a theoretical question. Someone has already tried. The line between rigorous science and pseudoscience is often drawn at the claim that human consciousness can directly affect physical reality. It evokes images of spoon-bending psychics and magical thinking. But what if we could strip away the aura of the paranormal and design a clean, controlled laboratory test? This is precisely what a group of researchers, including renowned physicist Sir Roger Penrose, attempted in a controversial series of experiments that began in the 2010s. The goal was to test whether focused human intention could influence the outcome of a quantum system. The double-slit experiment, often referred to as the quantum consciousness or intention experiment, was conceptually simple but technologically sophisticated. A standard double-slit apparatus was set up, firing photons or electrons one at a time towards a detector screen. This apparatus was fully automated and isolated, running for long periods to build up the classic interference pattern wave behavior. A separate group of human participants, located at a distance from the labs, sometimes in a different room, sometimes in a different country, were used as senders. These participants were shown a live video feed of the accumulating interference pattern on the detector screen. Their task was not to observe passively, but to intend. In randomized, computer-timed intervals, they were instructed to focus their mental attention and will the particles to behave like particles, to collapse the wave function and make the interference pattern disappear, forming two distinct clumps instead. The protocol was double-blind. The participants didn't know when the intention periods were active. The scientists running the physical apparatus didn't know when the intention periods were happening. The only thing linking the two was a computer program that randomly designated intention and control periods and coordinated the timing. If consciousness is merely a passive observer, as the Copenhagen interpretation might imply, then the participant's mental state should have zero effect. The quantum system should follow its normal probabilistic rules, regardless of what a person in another room is thinking. If, however, consciousness plays an active role in collapsing the wave function, if focused intention has a physical effect on quantum systems, then the data should show a statistically significant deviation during the intention periods. The interference pattern should weaken, indicating a shift towards particle-like behavior. The researchers, primarily those associated with the Global Consciousness Project and similar endeavors, have claimed positive results. They report small but statistically significant changes in the double-slit pattern correlated with the periods of focused intention. The variance, they argue, is beyond what random chance would allow. The scientific community's reaction has been, to put it mildly, dismissive. The criticisms are numerous and serious. Critics argue about potential flaws in the blinding process, data selection, or statistical analysis. The file drawer effect, where only positive results are published, is a major concern. Interpretation, even if the effect is real, is it consciousness causing it? Could it be some unknown, subtle physical interaction? The leap from a correlation to mind over matter is enormous. Replication. This is the gold standard of science. Mainstream labs have not been able to consistently replicate these results, which is the death knell for any controversial claim for most physicists. These experiments reside in the realm of fringe science. The evidence is not nearly robust or reproducible enough to overturn the standard model of physics. But let's engage in a thought experiment. Let's assume, for a moment, that the results are valid. What would that mean? It would mean that the observer effect is not a passive, automatic trigger. It would be an active faculty. It would mean that the degree of collapse could be influenced by the quality of attention, by focus, by intention. The universe would not just be waiting for any measurement to solidify. It would be responsive to the will of the observer. This would be the ultimate destruction of common sense. It would resurrect the ancient idea of a participatory universe, a concept championed by physicist John Archibald Wheeler. He envisioned a cosmos where we are not just spectators on a preset stage. We are actors, and our actions are observations, and our questions retroactively determine the past and shape the future. The universe becomes a self-excited circuit, awakening to itself through the consciousness that evolves within it. However shaky point toward this terrifying and magnificent possibility, they suggest that the final step in understanding quantum reality may not be a bigger particle accelerator, but a deeper understanding of the nature of our own awareness. We have traveled from the whispering atoms of panpsychism, through the quantum tunnels of the brain, to the direct intention of a mind upon a photon. We have progressively brought consciousness closer to the center of the cosmic drama. But now we must pull back. We must take the widest possible view and consider a principle that ties the existence of consciousness to the very laws and constants of the universe itself. This is the anthropic principle. The anthropic principle, in its simplest form, is the observation that the universe we observe must be compatible with the existence of observers. This sounds tautological, but its implications are profound. Physicists have discovered that the universe is balanced on a knife's edge. The fundamental constants of nature, the strength of gravity, the force of the strong nuclear interaction, the mass of the electron seem finely tuned. If any of these values were altered by even a minuscule amount, the universe, as we know it, would not exist. For example, if the strong nuclear force were just a few % stronger, all the hydrogen in the early universe would have fused into helium, leaving no fuel for stars. A few % weaker, and no elements heavier than hydrogen could form. No carbon, no oxygen, no life. If the force of gravity were slightly stronger, the universe would have collapsed back in on itself shortly after the Big Bang, slightly weaker, and matter would never have clumped together to form stars and galaxies. There are dozens of these cosmic coincidences. The universe appears to be rigged for life. Why? The weak anthropic principle, WAP, offers a pragmatic, almost Darwinian answer. It says, of course, we find ourselves in a universe capable of supporting life. We couldn't exist in one that didn't. It's a selection effect. Imagine a puddle waking up and thinking, this hole I'm in fits me perfectly. It must have been designed for me. The hole wasn't designed for the puddle. The puddle conformed to the shape of the hole. Similarly, we conform to the universe. There could be a vast, multiversian, endless froth of bubble universes, each with different physical constants, and we simply find ourselves in one of the rare, habitable ones. No fine-tuning required, just a statistical fluke. Then there is the strong anthropic principle, SAP. This is far more radical. It states that the universe must have properties that allow life to develop within it at some stage in its history. This must is controversial. It suggests that the laws of physics are not accidental. They are, in some sense, necessary for the production of observers. To understand why consciousness is such a formidable puzzle, we need to distinguish between the easy problems and the hard problem. The easy problems, coined by philosopher David Chalmers, are, well, not easy, but they are tractable by standard science. These include: how does the brain integrate information? How do we focus our attention? How do we discriminate and react to stimuli? We may not have all the answers, but we have a clear research program. Find the neural correlates, map the circuits, understand the computation. Then there is the hard problem, the problem of experience. Why and how do electrochemical processes in a lump of fatty tissue give rise to the feeling of the color red, the searing pain of a burn, the haunting beauty of a symphony? This is the problem of qualia, the raw, subjective, first-person quality of experience. You can describe the wavelength of light corresponding to red. You can map the optic nerve's firing pattern, but you can never capture the what dash it dash is dash like dash ness of seeing red from the inside. Materialism, the dominant worldview of science, asserts that consciousness is an emergent property of complex computation in the brain. Once the neural network reaches a certain threshold of complexity, poof, experience flickers into existence. But this is less an explanation and more of a declaration. How does complexity create subjectivity? Why doesn't all that complex processing just go on in the dark, like a supremely advanced computer, without an inner light turning on? This is where quantum physics re-enters the stage, not as a solution, but as a catalyst for a radical shift in perspective. For if the solid, objective world of materialism has been dissolved by quantum theory, then perhaps the idea of consciousness as a mere byproduct of a material brain is also on shaky ground. This leads us to the oldest and most controversial idea in the philosophy of mind: panpsychism. Panpsychism is the view that mind, or consciousness, is not something that magically appears at a certain level of biological complexity. Instead, it is a fundamental, ubiquitous feature of the universe, akin to mass, charge, or spin. The word itself comes from the Greek pan, all, and psyche, soul or mind. It does not mean that rocks are thinking deep thoughts or that electrons are happy or sad. It proposes that even the most basic units of reality possess some infinitesimal proto-conscious experience. An electron might have a dim, fleeting experience of being, a vague awareness of its environment, utterly alien to our own, but an experience nonetheless. The philosopher Gottfried Wilhelm Leibniz argued for this in the 17th century with his metaphor of the mill. Imagine a machine, a brain, whose workings we could walk into, like a mill. We would see only gears turning, levers pushing purely mechanical processes. Nowhere would we see an explanation for perception or consciousness. His point was that you can't get experience out of non-experience. If the fundamental building blocks of the universe are utterly insentient, then no matter how complex an arrangement you build from them, you will only ever get a more complex insentient machine. You can't get water from stones. Panpsychism flips this. It says the fundamental building blocks have a tiny bit of mind stuff. Then, consciousness as we know it isn't created from nothing. It is combined or integrated from these countless tiny bits of experience. The human brain doesn't generate consciousness. It orchestrates it. It is a complex receiver and integrator of the proto-consciousness inherent in its constituent particles. This idea seems ludicrous to common sense. It feels like a return to primitive animism. But from a quantum perspective, it starts to look strangely elegant. We already accept that particles have bizarre non-material properties. They are probability waves. They are entangled. They don't have definite locations until observed. The quantum world is already deeply weird and mental seeming. As Sir Arthur Eddington, the astrophysicist who confirmed Einstein's theory of relativity, famously said, "The stuff of the world is mind stuff." The universe, according to this view, is not a dead clockwork mechanism. It is a vast, evolving field of sentience, with complexity giving rise to richer and richer forms of experience. An atom has a whisper. A bacterium has a murmur. A human brain has a symphony. But this is philosophy. Is there any physics to back it up? To find it, we must turn to one of the greatest minds of the 20th century. A man who believed he had found the precise physical link between the quantum world and the conscious mind. Roger Penrose is not a fringe thinker. He is a titan of theoretical physics, a colleague of Stephen Hawking, a man who has reshaped our understanding of black holes and cosmology. He is also a staunch realist who believes that the wave function collapse is a real physical process and that it is driven by gravity. In the late 1980s, Penrose became convinced that consciousness could not be explained by classical computation. He argued, in his book The Emperor's New Mind, that human understanding, particularly in mathematics, involves a form of non-algorithmic insider grasping of Platonic truths that a mere computer, following a set program, could never achieve. He believed that something more was needed, something rooted in the fundamental laws of physics. He found that something in quantum gravity, the holy grail of physics. The attempt to unify quantum mechanics with Einstein's general relativity. Penrose proposed that wave function collapse is not caused by observation in the abstract, but by a specific physical threshold, when a quantum system's superposition becomes so massive that its space-time geometry becomes separated into two distinct realities. The universe's own fabric cannot sustain the strain of the superposition, and it spontaneously chooses one geometry over the other. This is his theory of objective reduction, or the collapse is objective, not subjective. It's a gravitational effect. But what does this have to do with consciousness? Penrose suspected that the brain had evolved to harness this objective reduction. But where in the brain could a quantum process be protected long enough to matter? The brain is warm, wet, and noisy, a terrible environment for maintaining the delicate coherence of a quantum state. Enter Stuart Hameroff, an anesthesiologist. Hameroff was fascinated by a question that is deceptively simple. How do anesthetics work? How do specific molecules, like ether or propofol, simply switch off consciousness while leaving non-conscious brain functions, like the brainstem's regulation of breathing, largely intact? He proposed that anesthetics must be acting on the very physical substrate of consciousness itself. That substrate, he argued, was not the neurons, but structures inside the neurons called microtubules. Microtubules are part of the cell's cytoskeleton, tiny cylindrical structures that act as scaffolding and highways for transporting molecules. In neurons, they are incredibly abundant and organized. Hameroff proposed that these microtubules were not just structural. They were quantum computers. Together, Penrose and Hameroff formulated the Orchestrated Objective Reduction Model, or ORCOR. The theory is breathtaking in its scope. It proposes the following. Within the microtubules of neurons, electrons become isolated in pockets shielded from the noisy environment. These electrons enter quantum superpositions, their wave functions spreading out, exploring multiple computational states. Simultaneously, this quantum coherence is orchestrated by synaptic inputs and the brain's biochemistry. Eventually, the mass of the superpositioned system reaches the Penrose gravitational threshold, and an objective reduction event occurs. The wave function collapses spontaneously. This collapse is not random. Penrose suggests it is influenced by non-computable Platonic information embedded in the structure of space-time itself, a glimpse at the fundamental level of reality. Each ORCOR event is a discrete moment of experience, a quantum blip of consciousness. The rapid sequence of these events across vast networks of neurons gives rise to the stream of our conscious awareness. In this model, your conscious thought is not a classical computer calculation. It is a cascade of quantum gravitational events, each one a direct interaction between the computational structure of your brain and the deepest geometry of the universe. The implications are staggering. It suggests that consciousness is a fundamental feature of the cosmos, accessed by biological systems via quantum processes. It explains the effect of anesthetics. They work by disrupting the quantum coherence in microtubules, preventing the ORCOR events from occurring. You're still alive, your brain is still functioning, but the quantum orchestra has fallen silent, and with it, the music of consciousness has stopped. Unsurprisingly, the ORCOR theory has been met with intense skepticism. Critics point out the immense difficulty of maintaining quantum coherence in the warm, wet brain. They argue that the brain is simply too hot for such delicate quantum states to survive for the necessary length of time. It remains a minority view, a beautiful, audacious, but unproven hypothesis. Yet, it represents a monumental effort to bridge the chasm. It takes the ghost of the observer and gives it a physical address, the microtubule. It dares to propose that our inner world is not separate from the outer quantum world, but is its most sophisticated and intimate expression. The most extreme interpretation of the SAP, one that brings us full circle to our quantum mystery, is the participatory anthropic principle proposed by John Wheeler. He took the lessons of quantum mechanics that the past is not fixed until observed in the present hand. Wheeler envisioned a participatory universe. He proposed a breathtaking cosmological model using a diagram he called the upside-down U. At the bottom left of the U is the Big Bang. The line curves up, representing the expansion of the universe and the formation of galaxies, stars, and planets. At the top of the U, life emerges, and eventually, conscious observers. Now, the line curves back down. This is the crucial part. The act of observation by these conscious beings, their measurements, their recording of data retroactively, gives reality to the universe's history, all the way back to the Big Bang. In this view, the universe only came into definite existence when its first conscious inhabitants evolved and began to look around and ask questions. We are not just living in the universe. The universe is living through us. The ultimate observer is the collective consciousness of all sentient beings, whose gaze weaves the scattered potentialities of the quantum past into a single, coherent, classical history. This completes the journey. We started with a single electron being observed in a lab. We end with the entire cosmos being observed by the life within it. The ghost in the machine was us all along. We are the universe's way of becoming aware of itself. So, we are left with our chapter's defining questions, now answered with a whisper that echoes across 13.8 billion years. We asked, is the universe conscious? The participatory anthropic principle answers, not yet, it is dreaming. And we are. The dream slowly waking up, and in doing so, waking the dreamer. We have reached the limit. We have fused the quantum with the cosmic, the particle with the person. But this union births a final, terrifying question, one that will consume our final chapter. If we are the universe becoming conscious, if our observations truly shape reality, what responsibility does that confer upon us? And what happens when our newly awakened power meets the darkest corners of human nature? In this final chapter, we descend from the cosmic heights into the human heart. We will explore a terrifying extension of quantum theory that suggests our collective attention is actively, and perhaps tragically, shaping our world. We will see how the very tools we use to observe the quantum realm could be used to construct a prison of absolute control. And we will be forced to gaze upon the darkest potential of a participatory universe, that the immense suffering, the injustice, the sheer chaos of our world is not happening despite us, but in some horrifying way because of us. The final destruction of common sense is this: we are not just the architects of our reality. We might also be the architects of our own hell. The idea that human consciousness can directly influence the physical world has long been the domain of mystics and shamans. But in the wake of quantum theory, a few scientists have dared to propose a framework for it. To understand this, we must introduce the concept of the noosphere. The term was coined by the chemist Vladimir Vernadsky and the philosopher-priest Pierre Teilhard de Chardin in the early 20th century. They envisioned the evolution of the Earth as a sequence of overlapping spheres. First, the geosphere, the inanimate Earth. Then the biosphere, the sphere of life. And finally, the noosphere, the sphere of mind. The noosphere is a postulated, planetary layer of thought, consciousness, and mental information, a collective human psyche enveloping the globe. For decades, this was pure poetry. But what if the noosphere is not just a metaphor? What if it has a physical, quantum substrate? Let's connect the dots from our previous chapters. We know that entangled particles can share information instantly. We know that the human brain, according to theories like Orkor, may leverage quantum processes. Now, extrapolate. If individual brains contain quantum coherent systems, is it so far-fetched to imagine that these systems could become entangled with one another through shared attention, emotion, and intention? Could there be a weak but real quantum entanglement that connects human minds, forming a literal, physical, social field? This is the controversial hypothesis at the heart of experiments like the Global Consciousness Project, GCP. The GCP, founded by psychologist Roger Nelson, operates a worldwide network of random number generators, RNGs. These are electronic devices that essentially flip a coin over and over, outputting a random sequence of ones and zeros. According to standard theory, their output should be pure noise. The GCP's hypothesis is that during major global events that focus the attention and emotion of millions of people, events like the 9/11 attacks, the death of Princess Diana, or even the New Year's celebrations, the collective coherence of the noosphere should increase. This mass-focused consciousness, they argue, should exert a slight but measurable ordering effect on the RNGs, causing their output to become slightly less random. The results, they claim, are, once again, statistically significant but controversial. They report that during such global events, the network of RNGs shows a tiny but persistent deviation from randomness. The sigma, a measure of statistical surprise, creeps up. It's as if the chaotic background hum of the world's mind suddenly develops a faint, coherent rhythm in the face of shared trauma or joy. The scientific mainstream remains deeply skeptical, citing the same issues of replication and methodology as the intention experiments. But let's, once more, engage the thought experiment. Let's assume the effect is real. The implications are staggering. It would mean that our minds are not isolated. We are nodes in a planetary network of consciousness, and our collective mental state has a faint, but real, telepathic-like influence on the physical world. Shared fear could literally inject a subtle order into the universe's chaos. Widespread love could, in principle, do the same. This is the bright side of the participatory universe vision of global unity and healing. But there is a dark side, a terrifying inversion. If our collective attention can create order, what does our collective inattention create? Or worse, what does our collective focus on negativity create? This leads us to a harrowing quantum interpretation of an ancient social phenomenon. The panopticon was a prison design conceived by the philosopher Jeremy Bentham in the 18th century. It featured a central watchtower surrounded by a ring of prison cells. The guards in the tower could see into every cell, but the prisoners could not see into the tower. The key was that the prisoners never knew if they were being watched at any given moment. Therefore, they had to assume they were always being observed, and thus regulate their own behavior accordingly. The mere possibility of observation became a tool of absolute control. Now, transpose this concept onto the quantum social field. In a participatory universe, what is the ultimate panopticon? It is us. We are both the prisoners and the guards. Every time we scroll through a news feed dominated by tragedy, conflict, and outrage, we are not just passive consumers. We are observers. We are focusing our attention, and in a quantum-informed model of the noosphere, we are thereby collapsing a wave of potential realities into a single, solidified fact. We are voting with our awareness for a world defined by that tragedy, that conflict, that outrage. Einstein argued this was impossible. No signal can travel faster than light. How could particle B know that particle A had been measured and instantly decide its own spin? He concluded that the only reasonable explanation was that the spins were predetermined. From the moment the particles separated, they carried with them hidden instructions like a pair of gloves. If you find a left-handed glove here, you instantly know the one over there is right-handed, not because of spooky action, but because it was always a right-handed glove For 30 years, this was a philosophical debate. Then, in 1964, a soft-spoken Irish physicist named John Stuart Bell found a way to test it. He derived a mathematical theorem, Bell's inequality, that showed a clear, testable difference between Einstein's local hidden variables and standard quantum mechanics. The essence of Bell's test is devilishly clever. It doesn't just check if the particles are correlated. It checks the strength of their correlation under different measurement settings. If Einstein was right, and the particles carried local hidden instructions, the correlation would never exceed a certain limit. If quantum mechanics was right, the correlation would be stronger. Violating this limit, building a working Bell test experiment, was a monumental challenge, finally achieved by Ailing Aspect and his team in France in the early 1980s. They created pairs of entangled photons and sent them in opposite directions to detectors that could, randomly and swiftly, change their measurement settings while the photons were in flight, ensuring no light-speed signal could communicate between them. The result was unambiguous. Bell's inequality was violated. Quantum mechanics was right. Einstein was wrong. There is no spooky action. There is. The universe is not. Entangled particles, once connected, remain a single, unified quantum system, no matter the distance between them. Measuring one immediately influences the state of the other. This isn't just a theoretical idea, it's a technological one. Quantum encryption and quantum computing are built on the proven reality of entanglement. This is a staggering blow to our common-sense notion of reality. It means that the universe, at its most fundamental level, is not a collection of separate, isolated objects. It is a deeply interconnected web. Separateness is an illusion. The space between you and the screen you're reading this on, the space between you and the farthest star, this space is not a passive void. It is filled with invisible, instantaneous quantum connections that bind the cosmos into a single, inseparable whole. We have now established two terrifying pillars of the quantum world. Reality is indefinite until measured. The problem of the observer. Reality is non-local. The problem of entanglement, individually. Each one shatters a piece of our classical worldview. But when you combine them, when you fuse the fuzzy particle with the spooky connection, you create an experiment so bizarre, so counterintuitive, that it seems to break time itself. We now arrive at the heart of the mystery. We have seen that observation defines reality. We have seen that entangled particles are connected across space. Now, we ask, what happens when we entangle these ideas with the flow of time itself? This brings us to the infamous delayed choice quantum eraser experiment. I want you to follow this closely because its implications are, I believe, the most philosophically devastating in all of physics. Let's return to the classic double-slit experiment. We fire photons, one at a time, at a barrier with two slits. Even though they are particles, they build up an interference pattern on the back screen, a telltale sign that each photon is going through both slits like a wave. Now, let's try to catch them in the act. We place a detector at each slit to figure out which path each photon takes. The moment we do this, the interference pattern vanishes. The photons, now being observed, behave like particles and go through one slit or the other, forming two simple clumps on the screen. The act of which path measurement collapses the wave function. Now, here is the delayed choice twist. What if we could make this measurement, but then, after the photon has already hit the final screen, we decide whether or not to erase that which path information? This sounds like science fiction, but it's possible using quantum entanglement. The setup is complex, but the logic is breathtaking. Imagine we don't send our original photon through the slits directly. Instead, we first fire a photon at a special crystal that creates a pair of entangled photons. We send one of these photons, the signal photon, through the double-slit apparatus towards our main detector screen. We send its entangled twin, the idler photon, off on a different path, towards a set of beam splitters and detectors that can either reveal which path the signal photon took, or scramble that information. Here is the sequence of events in time. The entangled pair is created. The signal photon goes through the double slits. Its wave function is in a superposition of going through both slits. The signal photon hits the final screen, but it does not make a definite mark yet. Its potential to land in any given spot is still just a probability. A fraction of a nanosecond later, the idler photon arrives at its own set of detectors. Now, the magic. The idler photon's path is configured so that depending on which detector it hits, the insane result is this. The pattern that appears on the main screen from the signal photon, whether it is a clump pattern particle behavior or an interference pattern wave behavior, is determined by what we later do with the idler photon. Let me repeat that. A decision made after the photon has already finished its journey and hit the detector determines how it behaved during its journey. It's as if you're watching a recording of a friend choosing to turn left or right at a fork in the road. Then, you press a button that decides whether the recording you just watched will show them hesitating and going both ways wave behavior, or confidently picking one path particle behavior. Your choice in the present is rewriting the past. This is the quantum eraser. It suggests that the past is not fixed. It is malleable. It is only finalized when a measurement, an observation, an irreversible record is made in the present. Until that moment, history itself exists in a state of quantum superposition. What does this mean for our observer? It suggests that observation isn't just about a conscious being looking at something. It's about the irreversible flow of information into the universe. It's about an event becoming real by being recorded in a way that could, in principle, be used to infer a fact. The universe seems to be a story that is written not from the first page to the last, but from the middle outward, with the ending influencing the beginning. We have chased the observer from the laboratory into the fabric of time itself. We started by asking what collapses the wave function. We ended by discovering that the collapse might retroactively define what the wave function was. So, we are left with our chapter's defining question, now sharpened to a razor's edge. We asked, does the world exist when you're not looking? The quantum eraser experiment seems to whisper a more terrifying question. Does the world ever exist in a definite state until a conscious mind, somewhere, somehow, finally takes note? We have pushed the role of the observer to its logical extreme. But this leads us to the final and most controversial frontier. If consciousness is so intimately tied to the manifestation of reality, could it be that consciousness is not a product of the brain, but a fundamental feature of the universe itself. We are about to cross the final frontier, the one that lies not in the cold vacuum of space, but in the warm, dark mystery of our own minds. We will explore a theory so radical it claims that every atom, every photon, every quark possesses a faint glimmer of what we call experience. We will follow a Nobel Prize-winning physicist down a path that links the structure of the universe to the nature of thought. And we will confront an experiment whose result suggests that the human mind can directly influence the fabric of reality on a quantum level. The question that has been building from the very beginning now demands an answer. Is the universe conscious? And if it is, what does it mean that a part of it has begun to look back at itself and ask that very question? The algorithms that curate our digital lives are not neutral. They are observation-enhancing engines. They are the architecture of the quantum panopticon. They amplify certain events, the most shocking, the most fear-inducing, the most divisive, and beam them into the conscious awareness of billions of people. In doing so, they are orchestrating a mass observation event, a global wave function collapse towards a reality of fear. Think of the world as a vast quantum probability wave. It contains potentials for peace, for breakthrough, for cooperation, and for war, for collapse, for hatred. Our collective observation is the measurement that selects which potential becomes real. When our attention is relentlessly funneled towards the negative, we are, en masse, collapsing the wave function into the darkest possible timeline. This is not a metaphor. If the GCP and the intention experiments hold even a grain of truth, then this is a physical process. Our 24/7 news cycle, our social media outrage machines, our obsession with celebrity scandal and political vitriol, these are not just reflections of a broken world. They are the very instruments that are breaking it. We are trapped in a feedback loop of our own creation. We observe the darkness, which solidifies it, which gives us more darkness to observe. The quantum panopticon is the realization that the ultimate tool of control in the 21st century is not a weapon, but a narrative. It is the power to direct the collective observation of humanity. Whoever masters this, be it a corporation, a government, or a malevolent AI, masters reality itself. They don't need to force you to do anything. They simply need to ensure you are always observing the world they want you to see, and your own consciousness will do the rest of the work, weaving that world into existence. This is the ultimate perversion of the participatory universe. It is a universe where the observer's power is hijacked to build a prison of perceived reality from which there seems no escape. But to understand the full depth of this horror, we must confront the most disturbing implication of all, the quantum mechanics of suffering. The problem of evil is the classic theological argument against an all-powerful, all-good God. If God is both, why does he allow immense suffering to exist? In a deterministic, clockwork universe, this is a moral problem. In a participatory quantum universe, it becomes a problem of complicity. Let's take the most extreme example. A child is born with a painful, incurable disease. In the old model, this is a random, tragic roll of the genetic dice, a terrible but meaningless event in an indifferent universe. In the participatory model, the implications are far more unsettling. The disease exists. It is a solidified reality. For it to be solidified, it must have been observed. Who observed it into being? The parents, the doctors, the suffering child themselves. This line of thinking leads to a place of profound cruelty, a form of spiritual victim-blaming of the most horrific kind. It cannot be the answer. Perhaps then we must consider the role of the collective observer. The child's suffering is a part of our shared reality. It is documented in medical journals, discussed in ethics classes, used in fundraising campaigns. It enters the noosphere. By being aware of it, by acknowledging it as a fact of our world, we, the global collective, are participating in the observation that maintains its solidity. This is the unbearable weight of the observer, our ignorance, our refusal to look away from the glittering distractions of modern life, our failure to focus our collective attention on healing and solutions. This inattention to light could be what allows the darkness to remain so stubbornly real. The potential for a cure exists in the probability wave, but it remains an unrealized potential because we, as a collective, have not collapsed the wave in that direction. We have not observed it into being with sufficient focus and intention. This transforms global suffering from a passive condition to an active, ongoing process in which we are all participants. The starving in famine-stricken regions, the victims of war, the casualties of systemic injustice, their realities persist, not just because of geopolitical failures, but because the global we has not mustered the coherent observational focus necessary to collapse the wave function toward a reality where their suffering ends. This is a heavy, perhaps even offensive, thing to suggest. It seems to add a layer of cosmic guilt to our already burdened shoulders, but it also contains the seed of our liberation. For if we are complicit in the creation of suffering through misdirected observation, then we also hold the key to its dissolution. The solution is not to stop observing. You cannot not observe. The solution is to change what you observe. It is to consciously, deliberately, and collectively redirect the spotlight of our awareness. This is not about positive thinking. This is about a fundamental reorientation of our observational stance towards the universe. It is the practice of what we might call intentional collapse. We stand at a precipice. The quantum revolution has handed us a power we are only beginning to comprehend, a power we have been wielding unconsciously and often destructively. The path forward requires that we grow up fast. We must evolve from passive witnesses to conscious co-creators. We must develop an ethic of observation. What would such an ethic look like? First, it begins with individual responsibility. It means becoming acutely aware of where we place our attention. Every click, every share, every hour spent consuming fear-based media is not a neutral act. It is a tiny vote, a mini-collapse, in the direction of that reality. The ethic of observation demands media literacy and conscious consumption. It asks, by observing this, what kind of world am I helping to solidify? Second, it requires collective intention. This is where the fringe experiments, for all their flaws, point towards a crucial truth. If focused intention can nudge a double-slit pattern, what could the focused intention of millions, directed towards peace, healing, and innovation, achieve? This is the rationale behind global meditation events, prayer circles, and mass visualizations. They are not just spiritual exercises, they are potential quantum engineering projects on a planetary scale. They are attempts to create a coherent, ordering pulse in the noosphere to collapse the wave function towards a more benevolent reality. Third, it forces a revaluation of our technology. Our digital tools are currently designed to capture and commodify attention, often by exploiting our basest instincts for outrage and fear. An ethic of observation would demand that we redesign these technologies to serve our highest values. Imagine social media platforms whose algorithms are optimized not for engagement, but for empathy, not for polarization, but for connection, not for highlighting chaos, but for showcasing solutions. These platforms would become engines for intentional, positive collapse. This is the final practical application of quantum theory. It is not just about building better computers. It is about building a better world. The next great leap in physics may not be a new equation, but a new understanding of the link between consciousness and reality, and the moral framework we build around it. We are the first generation to be presented with this evidence, however tentative, and this responsibility. We are the primordial neurons of a waking planetary mind, flickering with the first awful awareness of our own power. The chaos of our era is the birth pang of this awakening. So, we end our journey where we began, with a question. But it is no longer a question of physics, it is a question of choice. We have destroyed the common sense of a dead mechanical universe and revealed a living, responsive, and participatory one. The final question, the one that now rests in your hands, in your eyes, in your very awareness, is this. Now that you know your gaze has power, what will you choose to look at? Will you look at the division, and by seeing it, give it strength? Or will you look at the connection, the beauty, the solutions waiting in the wings of potentiality, and by seeing them, will them into being? The universe is a quantum wave of breathtaking possibility. It is waiting for your answer. This final chapter is not a theory, it is a manual. It is a transition from quantum philosophy to quantum praxis. We will synthesize every thread from the double slit to the newspherent, actionable framework. We will explore the documented real-world effects of mass intention. We will decode the mechanisms of what I will call conscious collapse, and we will lay out the first principles for a new science of reality creation. The question that has driven us is no longer what is reality, but how do we, together, build a better one to build? We need a blueprint. The scattered, controversial data from the fringes of science must be organized into a solid foundation. Based on everything we've explored, I propose that the act of conscious collapse rests on 5 interdependent pillars. These are not proven laws, but a working model derived from the logical implications of a participatory universe. Governance, policy would be designed not just for material outcomes, but for its impact on the collective consciousness. A key metric for any policy would be, does this promote fear, division, and powerlessness, or does it foster hope, connection, and agency? The latter would be chosen, as it creates a coherent noosphere capable of solving complex problems. Technology, our devices and AI would be re-engineered as intention amplifiers. Imagine a social network whose algorithm is designed to connect you with people who share your positive aspirations, or an app that helps you join a mass synchronized meditation for a specific global goal. Technology becomes a scaffold for conscious evolution. This is not a utopian dream. It is the logical next step for a species that has discovered it lives in a participatory universe. The alternative is to remain as we are, a collection of chaotic, conflicting observers. accidentally collapsing a world of our own collective nightmare, wondering why things keep getting worse. The choice is that stark. The data from the quantum lab to the sociological study points in one direction. We are the universe's consciousness, and we are at the stage in our development where we are becoming aware of our own creative power. This is our adolescence. It is messy, dangerous, and filled with potential. We have reached the end of our exploration. We began by destroying the common sense of a dead universe. We end by embracing the uncommon sense of a living, responsive one. The final lesson of quantum physics is not a formula. It is an invitation. You are not a spectator. You are a creator. Your attention is your most powerful tool. Your world is your masterpiece in progress. So, I leave you not with a final answer, but with a first principle. A principle to carry forward from this moment, to guide your every observation, your every intention, your every action. Observe, not as the world is, but as you know, in your deepest heart, it can be. This final chapter is not a theory. It is a manual. It is a transition from quantum philosophy to quantum praxis. We will synthesize every thread from the double slit to the new coherent, actionable framework. We will explore the documented real-world effects of mass intention. We will decode the mechanisms of what I will call conscious collapse, and we will lay out the first principles for a new science of reality creation. The question that has driven us is no longer what is reality, but how do we, together, build a better one? The synthesis, the 5 pillars of conscious collapse to build. We need a blueprint. The scattered, controversial data from the fringes of science must be organized into a solid foundation. Based on everything we've explored, I propose that the act of conscious collapse rests on 5 interdependent pillars. These are not proven laws, but a working model derived from the logical implications of a participatory universe. The substrate of potentiality. The quantum field, this is the raw material. The universe is not a collection of things, but a dynamic, infinite field of overlapping probability waves. Every possible event, from the formation of a star to a specific thought in your mind, exists as a potentiality within this field. It is the uncarved block of marble from which reality is sculpted. This is the world described by the Schrödinger equation before collapse, a shimmering symphony of maybes. The instrument of collapse-focused consciousness, this is the chisel. A conscious mind, through the act of specific, focused attention, provides the measurement that collapses a specific potential into a specific actuality. This is not passive seeing. It is active looking. It is attention imbued with intention. The observer effect is, in its highest form, the intention effect. The clarity, energy, and emotional charge of the intention determine the coherence and power of the collapse. The amplifier resonant entanglement, a single mind, is a powerful instrument, but interconnected minds are a world-shifting force. This pillar states that consciousness is non-local and can entangle, much like particles. When multiple conscious agents focus on the same intention with emotional and cognitive coherence, their observational power does not just add together, it multiplies. They create a resonant field in the noosphere, standing wave of intention that dramatically increases the probability of a specific collapse occurring in the shared reality. This is the principle behind the global consciousness. Projects, data, and the theoretical basis for the power of mass prayer or meditation. To bridge emotional and symbolic conduits, the quantum field does not speak English or process logical propositions. It responds to the raw language of existence, emotion, symbol, and archetype. A deeply felt emotion of gratitude is a more potent collapse signal for abundance than the intellectual thought, "I want to be rich." A powerful visual symbol of peace can anchor a collective intention more effectively than 1,000-word treatise. Our emotions and the symbols we resonate with are the transducers that convert our mental intentions into a language the quantum field can understand and act upon. The law of focus, what you observe, solidifies. This is the foundational ethic, now stated as a principle of action. The probability wave that collapses is the one upon which the most focused attention individual or collective is placed, period. It is agnostic to good or evil. It simply responds to the energy of observation. Therefore, the primary task of a conscious creator is to manage focus. Fighting against what is, with rage and resistance, is still a form of powerful, focused observation on what is, thereby reinforcing it. The only way to change a solidified reality is to withdraw your focus from its current state and place it, with greater passion and coherence, upon the desired state. This 5-pillar model gives us a framework. But is there any evidence that this isn't just elegant fantasy? To answer that, we must leave the lab and look at the world itself. Viewed through this new lens, the evidence case studies in conscious collapse, smoking gun for conscious collapse, will not be found in a single, perfect physics paper. It will be found in the aggregate of anomalous data from fields as diverse as sociology, psychology, and medicine, when viewed through the quantum paradigm. Let's examine a few compelling case studies. The Maharishi effect in the 1970s. Followers of Maharishi Mahesh Yogi proposed that if even a small fraction of a population, approximately the square root of 1%, practiced transcendental meditation together, it would produce a measurable effect of reduced crime and social violence in the surrounding community. Dozens of studies were conducted in cities around the world. The results, published in peer-reviewed journals like the Journal of Conflict Resolution, claimed statistically significant reductions in violent crimes, sometimes by over 20% during the periods of group meditation. The skeptics cried correlation, not causation. But from the perspective of conscious collapse, this is exactly what we would predict. A coherent group, focusing on an intention of peace, created a resonant field that subtly collapsed the probability wave of social reality away from violence and toward harmony in their locality. The placebo and nocebo effects in medicine. The placebo effect is well documented. A patient's belief in a treatment can trigger real, measurable physiological healing, even if the treatment is a sugar pill. The nocebo effect is its dark twin. A patient's belief that they will suffer side effects often makes them do so. Materialism struggles to explain this. The quantum model explains it elegantly. The patient's deeply held belief, their focused intention about their health acts as a powerful observational collapse. It tells the body's quantum mechanical processes, from protein folding to neural regulation, to actualize the reality of health or sickness. The pill is just a symbol. The real catalyst is the conscious expectation of the observer. The rise and fall of social movements. Why do some social movements fizzle out while others change the world? The quantum model offers an answer. A movement based on fighting against an injustice often burns out because its focus is on the problem it hates, thereby giving it energy. A movement that successfully captures the public imagination is one that paints a vivid, compelling picture of a new future. It shifts the collective focus. The civil rights movement didn't just say, "Stop racism." It declared, "I have a dream." It gave the noosphere a powerful, emotional, symbolic image to focus on a specific potential to collapse. The collective observation of that dream by millions began to weave it into reality. These are not proof, but they are a pattern that consistently shows focused, coherent intention, especially when shared, has a mysterious but measurable effect on the physical and social world. The mechanism for this effect has been a mystery. The 5 pillars of conscious collapse provide that missing mechanism. The substrate of potentiality, the quantum field. This is the raw material. The universe is not a collection of things, but a dynamic, infinite field of overlapping probability waves. Every possible event, from the formation of a star to a specific thought in your mind, exists as a potentiality within this field. It is the uncarved block of marble from which reality is sculpted. This is the world described by the Schrödinger equation before collapse, a shimmering symphony of maybes. The instrument of collapse-focused consciousness. This is the chisel. A conscious mind, through the act of specific, focused attention, provides the measurement that collapses a specific potential into a specific actuality. This is not passive seeing. It is active looking. It is attention imbued with intention. The observer effect is, in its highest form, the intention effect. The clarity, energy, and emotional charge of the intention determine the coherence and power of the collapse. The amplifier resonant entanglement. A single mind is a powerful instrument, but interconnected minds are a world-shifting force. This pillar states that consciousness is non-local and can entangle, much like particles. When multiple conscious agents focus on the same intention with emotional and cognitive coherence, their observational power does not just add together, it multiplies. They create a resonant field in the noosphere, standing wave of intention, that dramatically increases the probability of a specific collapse occurring in the shared reality. This is the principle behind the global consciousness projects, data, and the theoretical basis for the power of mass prayer or meditation, that bridge emotional and symbolic conduits. The quantum field does not speak English or process logical propositions. It responds to the raw language of existence, emotion, symbol, and archetype. A deeply felt emotion of gratitude is a more potent collapse signal for abundance than the intellectual thought, "I want to be rich." A powerful visual symbol of peace can anchor a collective intention more effectively than 1,000-word treatise. Our emotions and the symbols we resonate with are the transducers that convert our mental intentions into a language the quantum field can understand and act upon. The law of focus, what you observe solidifies. This is the foundational ethic, now stated as a principle of action. The probability wave that collapses is the one upon which the most focused attention individual or collective is placed, period. It is agnostic to good or evil. It simply responds. to the energy of observation. Therefore, the primary task of a conscious creator is to manage focus. Fighting against what is with rage and resistance is still a form of powerful, focused observation on what is, thereby reinforcing it. The only way to change a solidified reality is to withdraw your focus from its current state and place it, with greater passion and coherence, upon the desired state. This 5-pillar model gives us a framework. But is there any evidence that this isn't just elegant fantasy? To answer that, we must leave the lab and look at the world itself. Viewed through this new lens, the evidence case studies in conscious collapse. Smoking gun for conscious collapse will not be found in a single, perfect physics paper. It will be found in the aggregate of anomalous data from fields as diverse as sociology, psychology, and medicine, when viewed through the quantum paradigm. Let's examine a few compelling case studies. The Maharishi effect in the 1970s. Followers of Maharishi Mahesh Yogi proposed that if even a small fraction of a population, approximately the square root of 1%, practiced transcendental meditation together, it would produce a measurable effect of reduced crime and social violence in the surrounding community. Dozens of studies were conducted in cities around the world. The results, published in peer-reviewed journals like the Journal of Conflict Resolution, claimed statistically significant reductions in violent crime, sometimes by over 20% during the periods of group meditation. The skeptics cried correlation, not causation. But from the perspective of conscious collapse, this is exactly what we would predict. A coherent group, focusing on an intention of peace, created a resonant field that subtly collapsed the probability wave of social reality away from violence and toward harmony in their locality. The placebo and nocebo effects in medicine. The placebo effect is well documented. A patient's belief in a treatment can trigger real, measurable physiological healing, even if the treatment is a sugar pill. The nocebo effect is its dark twin. A patient's belief that they will suffer side effects often makes them do so. Materialism struggles to explain this. The quantum model explains it elegantly. The patient's deeply held belief, their focused intention about their health acts as a powerful observational collapse. It tells the body's quantum mechanical processes, from protein folding to neural regulation, to actualize the reality of health or sickness. The pill is just a symbol. The real catalyst is the conscious expectation of the observer. The rise and fall of social movements. Why do some social movements fizzle out while others change the world? The quantum model offers an answer. A movement based on fighting against an injustice often burns out because its focus is on the problem it hates, thereby giving it energy. A movement that successfully captures the public imagination is one that paints a vivid, compelling picture of a new future. It shifts the collective focus. The civil rights movement didn't just say, "Stop racism." It declared, "I have a dream." It gave the noosphere a powerful, emotional, symbolic image to focus Anna's specific potential to collapse. The collective observation of that dream by millions began to weave it into reality. These are not proof, but they are a pattern that consistently shows focused, coherent intention, especially when shared, has a mysterious but measurable effect on the physical and social world. The mechanism for this effect has been a mystery. The 5 pillars of conscious collapse. provide that missing mechanism, the practice, a user's guide to reality, knowing the theory is useless without practice. How do we, as individuals and as a collective, actually do this? How do we become conscious collapsers? The process can be broken down into a repeatable discipline. Define the desired collapse with specificity.